based on joint work with Kyle Hayden and Lisa Piccirillo. An alternative title for this talk is Every Slope is Non-Characterizing for some knot. So a slope is a Dehn surgery slope, and a slope is non-characterizing if you can find a pair of knots which share the same surgery of that slope. So the outline of this talk, first I'm going to give you a bit of background about this problem, and then the second part is going to be constructing a homeomorphism like this, and the last part will be showing that we actually have different knots in our homeomorphism. So Dehn surgery is a way to get from a link in the three-sphere to a three-manifold. So we have this link, we need to do Dehn surgery of, we can pick any slope for each component of the link, and we build a three-manifold. Licorice and Wallace showed that, in fact, all closed-oriented three-manifolds can be obtained in this way. So it's a really useful construction. However, these surgery descriptions are highly non-unique. So, for example, if we just look at the three-sphere, this could be expressed as surgery on a hop link with slopes 0 on both components, or it could be expressed as surgery on just an unknot with slope 1, or even a rational slope 1 over n. These are all different ways of expressing the three-sphere as surgery on a link. So what we want to do is restrict the question so that instead of looking at surgery on links, we're actually just going to look at surgery on knots. And so for any rational slope, we're going to define the Dehn surgery function to be the function which goes from the set of knots in S3 to the set of closed-oriented three-manifolds with the right homology, and the function is going to take a knot to surgery on that knot of the given slope. So in 1978, Gordon conjectured that this Dehn surgery function is neither surjective nor injective. The surjectivity part was proven by Gordon and Lukey in 1989. So they basically showed that if you have a reducible surgery on a knot, then it must have a lens space some n. So if you had some other reducible surgery, then you wouldn't be able to obtain that as surgery on a knot. And our main result is that is the injectivity part. So we show that for any P over Q, this function is non-injective. So we can always find a pair of distinct knots sharing the same surgery of that fixed slope. And there has been some previous work done on this before. So for example, the case where P equals 1, this is due to licorice. The case where Q is equal to 1 is due to, I think, brakes and Akbalut. And there's plenty of examples of knots sharing the same surgery of an integer slope. Kawauchi showed that if you have P congruent to 1 mod Q, then you can always find such a pair of knots. And in fact, Baker and Motegi asked in 2018 if you need this condition. So if it's only slopes with P congruent to 1 mod Q, for which the surgery is non-injective. And so we've answered this question and said that no, in fact, for any P over Q, the function should be non-injective. So the strategy, as I mentioned earlier, we're going to fix a slope P over Q. In most of the talk, we'll be talking about how to construct this homeomorphism between surged manifolds. And then in the last part, we'll be showing that, in fact, these knots are really different knots. And the way we're going to do that is, the first part is going to be using RBG links and dual knots. So we're going to look in some detail about what it means to be a dual surgery. And then the last part will be using an invariant called the zeroth Homfley polynomial. Okay, so an RBG link is going to be a rationally framed three-component link, colored red, blue, and green, such that there exists homeomorphisms which cancel pairs of surgeries. So we have a red component with framing little r. We have a blue component with framing little b. And then we also have this green component with framing little g. And we can see here that there are these two homeomorphisms, which basically, so the first one says that if you only do surgery on the red component and the blue component, then they cancel out and you just get back S3. And what happens to the green component when you do that? Well, you have to track how it behaves under this homeomorphism that goes to S3. So the green component, it might be a bit changed up, but this homomorphism is going to take green to some knot in S3, in this new S3, and the framing might change now. So it's still a knot because we've cancelled red and blue. Green is still going to be like an embedding of the circle into this new S3. So we're going to call this new knot KG. And then the RBG link also has this property if you do the red and the green surgeries and you just leave the blue one untouched. So we also have this homeomorphism to S3, which is going to take the blue component to some other knot, which we'll call KB, that lies in S3. And again, we possibly have a change of the framing. So this is going to be useful for us because if we now do the surgery on the third component that we'd forgotten about, then we're going to obtain surgery on a knot in two different ways, right? So if we do all three of these fillings, red, blue, and green, then one way to think about that is you've done the surgeries on red and blue, they're cancelled, and then you've got surgery on KG, or you can reverse the roles of blue and green. So we end up with these two homeomorphic surgeries on knots. So what we want to show is we basically are going to use this construction. We're going to find some pair of knots, KB and KG, where we have the new framings both need to be our fixed P over Q. And we also need to show that KB and KG are different. So this strategy has been used before in the case where P over Q is an integer. So for example, in Lisa Piccirillo's proof that the Conway knot is not slice, she had this B prime equals G prime equals 0 and found a pair of knots. So she chose, or by construction, KB was the Conway knot, KG was some other knot, and B prime equals G prime equals 0. So they shared a 0 surgery. So what we want to do is like use the same sort of strategy, but instead of for integers, we want to do it for the rationals. Any questions so far? Okay, so the way we're going to construct our RBG link, we need somehow to have these cancelling pairs of surgeries, and they're going to have rational coefficients. So one way to do that is by using this idea of dual knots. So we're going to do our Dehn surgery on a knot K. So here's just a schematic showing what it means to do Dehn surgery. So here we have the exterior of some knot K in S3. When we do Dehn surgery, we're going to be gluing in some solid torus, which I'll call V, with some map, which is a homeomorphism of the torus. So this is how we get surgery on a knot of some slope. Yeah. Yeah. Sorry? Can I break the chalk? Yeah, sure. I didn't know that's what makes it squeak. Okay, so what is the dual knot? The dual knot is going to be the image of the core curve of this torus. So here I'm drawing the core, sorry, of this solid torus V. When we glue this into here, the core knot is going to follow along. And we do the surgery, and we've glued in the solid torus, and now the core of the solid torus becomes a dual knot inside this new 3-manifold that we've built. So the idea is to make a cancelling pair of surgeries. We want to first do this Dehn surgery on our knot, and then we want to do some other surgery on the dual knot to get back to S3, right? How's that going to work? Well, one thing that I first want to tell you is that this core knot, it can be pushed. So it'll be easier to view it if instead of sitting inside this solid torus that we've glued in, we can actually push it so that it lies on the outside of this torus. And then it's going to be some curve sitting on the torus. So this is going to tell us that actually the dual knot is going to look like some cable of our original knot. Okay, and you can keep on doing this whenever you take duals. So here's a picture that shows that. Your core knot can either be thought of as sitting inside the surgery torus, or you can push it outside and it's going to become a cable. So let's think about this in terms of we want this like P over Q surgery. So what that means is that this gluing matrix, if we pick a basis for our solid torus, so we're going to choose a meridian and some longitude, but it will be a fixed longitude. If we do this, then we can actually express our matrix A as a 2x2 matrix, where the first column is going to be PQ, because that's going to tell us where the meridian goes. That's the definition of Dehn surgery. And then the second column is going to tell us where the longitude goes, and that's our RS. And it's going to be important for us to actually track what happens to the longitude. So even though you don't need that information when you normally do Dehn surgery, it's going to be useful for us. And the reason is that this core curve sitting in the solid torus is actually isotopic to a longitude. So when we push it outside of the solid torus and it becomes some cable, we actually know what the cabling parameters are of this cable, because it's going to come from where the longitude goes. So in fact, this dual knot, K star, is going to be an RS cable of the knot K that we started with. Does that make sense? Okay, great. So yeah, our matrix holds these two very important pieces of information. I'm sorry, I drew these in the wrong colors. Okay, so now we need to do some surgery on the dual knot, which is going to cancel this out. So we've done our first surgery. Now we need to do some surgery on this, which is going to give us back S3. The way that we do that is, so if we want to do surgery on this red knot, what that means is we drill out a neighborhood of it. And then we need to do Dehn surgery by gluing in some other solid torus. So this is our second surgery that we're going to do. And to make them cancel out, well, if this was glued in by a matrix A, then this one should just be glued in by a matrix A inverse, right? Because then you have two surgeries and the composition of them is just doing nothing. The only thing is that since we're thinking of our dual knot as a cable, we want to make sure that the Dehn surgery is expressed with respect to the correct basis, the one that actually comes from the knot. So if we draw our complement of K dual, and we think of this map as going from the solid torus into the complement of K dual, this is going to be encoded by some other matrix A star, which is the one that I've written here. And this is literally just, it's A inverse, but with some change of basis accounted for. And that's going to give us, again, the first column will be the surgery slope that we need for K dual, and the second column is going to tell us what happens to a longitude, or equivalently, what's going to happen to the core of the next knot along. right? So we have this pair of cancelling surgeries on blue and red, and if we repeat the process, then we can get a pair of cancelling surgeries on red and green. So we just do exactly the same thing again. We're going to delete a neighborhood of the core of red, and we're going to do a surgery where we glue in this very skinny solid torus, and it's going to have to cancel with this gluing. So this one's going to have to be encoded by a matrix A. But again, if we're thinking of it with respect to the basis coming from the knot, then we're going to have to slightly change what this matrix looks like. So our K double dual is going to be a cable of the previous thing. So a QR squared P cable of the previous thing, because it comes from the second column of this matrix. And when we write this A matrix with respect to the basis associated to this cable of a cable, this is what we end up with. Any questions? Okay, so to summarize, we've constructed an RBG link where we've started with just a blue knot, some blue knot, which I've drawn to be the unknot here. And then our red is some cable of the blue, so it's some RS cable. And then the green one is going to be some cable of the red one, so it's going to be like an iterated cable. And by our construction, the red and blue surgeries are going to cancel, and also the red and green surgery is going to cancel. But the problem with this RBG link is that because the dual of a knot is just the original knot, what that means is that when you follow through the homeomorphisms and you try to find out what KB and KG are going to look like, they're actually just the same, and in particular in this case, they're actually both just the unknot. So we haven't done anything particularly useful here. We've just found some way of expressing P over Q surgery on the unknot in two different ways. So this is not particularly helpful, but we can actually just make a slight modification and make our knots different. So the way we want to do that is we need to introduce some interaction between blue and green. So we have our blue component and we have our green component. And we want to make them interact in some way which isn't going to affect all of our framing computations. So they're going to interact in this box. And we want to do it in such a way that like the linking between blue and green is 0. We also want to make sure that there's some kind of an asymmetry going on here. So it needs to be some kind of an asymmetry which is going to affect the KB in one way and the KG in a different way. So here's a picture of how we do that. We're basically going to take a band sum of blue with some satellite of the meridian of green. And it needs to be a special kind of satellite knot. So our satellite operator, it needs to be unknotted, but asymmetric in some way. So the first thing you might try is like a Whitehead operator, because this is very nicely unknotted. But the problem with this is that if you exchange the components, so one should be blue and one should be green, then you get back the Whitehead link again. So this isn't going to be quite good enough. What we do instead is we take a Whitehead double of a Whitehead double. So we're going to compose two Whitehead doubles where one of them has 2 clasps, one of them has 1 clasps. And if you reverse this now, so this picture shows, I've just done an isotopy here, and it's basically ended up taking blue back to how it was, and green has become a band sum with some satellite of the meridian of blue. And the satellite is going to be like what happens if you reverse this pattern. So the second satellite operator is going to be the 2-clasped Whitehead double composed with the 1-clasped Whitehead double. And these are not the same pattern. And if we now do the cancellation to get our knots, So you can thank Kyle for these beautiful drawings. You can see that, so I won't go into the details of why this works, but you now have some extra bit to KB, like you take this band sum with some other quite complicated knot, whereas if you do the version for KG, you get the same sort of thing, but the only difference is in like these patterns which appear in the definition. So one of them has this PB, and one of them has this PG. So these are our two knots, which I claim are actually different. Does anyone have any questions so far? Okay, so we have our two knots. So we've done this part. We found KB and KG sharing the same surgery. Oh, and I should also mention that they have the same slope, and this is by construction. This is because we specifically chose this matrix A, where the first column was P over Q, and over here we also have the matrix A appearing again, so we get P over Q for the second surgery as well. So yeah, it remains to try and tell these knots apart. We're going to use an invariant that comes from the Homfley polynomial. So the Homfley polynomial is defined by a Skane relation. And in fact, it admits a very nice decomposition. So if you collect together all the terms with a common power of z, then you have these ith polynomials, which are polynomials in terms of v, which come with each power of z. And we'll be particularly interested in the I equals 0 case. We're going to use this to distinguish our knots. So this is like the constant term with respect to z. So we're going to show that when p is bigger than 1, the 0th Homfley polynomials of these two knots are not going to be the same. We couldn't quite do it when p is less than or equal to 1, but this is okay because these cases have already been solved. So there's a few key properties of this invariant. One of them is that it obeys its own Skane relation. So the Skane relation, we orient our link, and we have this triple where we have L plus looks like this, L minus looks like this, and L0 looks like this. And the value that you get on the right-hand side, it depends whether the number of components in L0 is going to be higher or lower than the number of components in one of the others. There's also a very nice linking formula, which basically says that if you're looking at the Homfley polynomial of some link, then you just need to take the product of all of the components, the polynomial for all of the components of the link, and then you have to account for this total linking number of L. So that's basically the sum of all the linking numbers between the different components. So it only depends on like the linking numbers rather than like what the actual linking looks like. Okay, so it was difficult to compute what the actual absolute value of this polynomial was for these very complicated knots, KB and KG, which we have. But in fact, the difference between them, we could compute that. And the way we did it was by, so in these patterns, wherever we saw a Whitehead clasp, that gave us like an L plus. So if we look at this crossing here, this is going to look like L plus, and then you can resolve it so L minus is going to look like this, and that's going to allow us to pull some things apart very easily, and L0 is going to look like this. So in every step, these will have like one component, and then this becomes like a two-component link for L0. So once we have a two-component link, then we can apply like this linking formula and split everything into knots again. And we keep on doing this process until we end up with some very trivial knots. And these are the ones that appear in the formula. So One of them is not important. The other one is exactly the cable of red which appeared in the description of our knots. So if I just go back for a moment to the description of the knot, you have this cable of the red appearing somewhere as part of this band sum. And the same in green, you also have this cable of red appearing somewhere. And this is, the Homfley polynomial of this knot is what appears in the difference. So this is going to be our f of v here. And if we want to show that the difference between the Homfley polynomials is not the zero polynomial, we just need to show that like none of these factors is the zero polynomial. So essentially, all we need to do is show that like f of v can never be a unit in the Laurent polynomial ring. And we do that by saying we choose our parameters so that this cable of red is a positive braid knot, and then we show that for any positive braid knot, the polynomial can't be a unit, and then we can deduce that none of these factors in the difference are zero, and so we have this non-trivial difference between the two polynomials, and therefore the knots must actually be different. So I think that's everything I had to say. They're not satellite knots because there's this like band sum with the unknot that you take at the end. So if I go back to the picture, so this part is a satellite knot, but I think when you take the band sum with the other part, there's no longer any like incompressible torus that you can see. So I think they should be hyperbolic knots. Oh, so when you like add the modification in here? So basically, like because the linking between the blue and green is zero, it's not going to affect like the way that the framings behave in any way. So the framings in this one are going to be like exactly the same as with the other one, and then yeah, it's basically like because it's like it's almost no interaction. So you end up with something that is still an RBG link. So one way to see it is like if you deleted blue from the picture, then actually red and green were going to look exactly as they were before, so they're still going to cancel. And then the same goes the other way around. If you delete green from the picture, then red and blue are going to cancel in exactly the same way as before. I haven't really thought about that, but I imagine you can get quite a range of things. Like, I mean, one thing you could do is this blue component doesn't even have to be the unknot. It could be some other knot as well. So probably you can get quite a range of things, but yeah, good question.